Okay, our next speaker is Austin Crabtree from Kansas Beta. He will tell us about what is a sandwich fuzzy approach.
All right. Well, hello, everyone. I'm Austin Crabtree from Emporia State. And today I'm here to talk to you about an internet that has been a debate that has been raged over the internet for off and on for quite a while now. And that is, what is the definition of a sandwich? And we're going to look at this through a slightly unique view using a rather interesting branch of mathematics called fuzzy mathematics. Wait. No, there's no way this is right. Mathematics is never this cute and cuddly. There it is. That's closer to what I've been looking at for the past couple of months. All right. So to understand fuzzy mathematics, we first need to talk about its building block, and that is the fuzzy set. And to understand fuzzy sets, we first need to go back and talk about what ordinary sets look like and how they behave, or as a fuzzy mathematician would call them, crisp sets. Thought that was a fun little terminology. So we all know what regular sets regularly look like: a bunch of elements put inside a bunch of curly brackets. Use set builder notation or just list the elements. And a subset of a universal set is just some elements from that universal set, could be all or some of them. But people don't usually use the second type of how to describe subsets in a universal set, and that is a characteristic function. So what the characteristic function does is it takes elements from a universal set and it maps it into the set 0, 1, only including 0 and 1, in such a way where I give it an element in the universal set, plug it into the characteristic function, and it's going to spit out 1 if it's in the subset A and 0 if it's not in the subset A. So 1 in the set, 0 not in the subset. And now with this idea of a characteristic function in mind, we can define a fuzzy subset in a similar way using a characteristic subset. So we're going to let U be a universal set, and we're going to define a fuzzy subset to be the characteristic function that maps the universal set into a closed interval 0 to 1. So before we were just mapping it to the elements 0 and 1, so it either is going to be in the set or isn't, but now we're mapping it to the entire closed interval. So it could maybe be a half inside the set or 3/4 inside the set, where 0 and 1 still represent, like, if it's 0 membership to the fuzzy set, it's not in the set. And if it's 1, then it's 100% in the set. But if it's a half, then it's maybe like 50% inside the set. And we call this A, the membership function, and we call A of X the degree to which X belongs to the fuzzy subset A. So now that we have this fuzzy set, most of mathematics is built on set theory. So we can change a whole bunch of mathematics using just fuzzy sets. We can talk about like fuzzy algebra. We can talk about fuzzy statistics and probability, even fuzzy geometry. Don't all those look terrible? But instead, we're going to use it for a little more recreational use, and that is to define sandwiches. So we're going to look at our main example for today. So we're going to let U of F be the set of all foods. And we are going to define the fuzzy subset S to be the set of all sandwiches on the set of all foods. So usually in a characteristic equation in normal sets, we ask, is an element in a subset or is it not in a subset? But with fuzzy mathematics, we now ask the question, to what degree are the elements inside our subset? So we're going to ask, like, to what degree is a food inside the set of sandwiches? So let's look at a few examples. Peanut butter and jelly sandwich. If your definition of a sandwich does not put this near 100% inside the set, you got to change that. You got to fix that. It's a peanut butter and jelly sandwich is mostly a sandwich. I guess there's an argument for it not being. But yeah, so how we would write this is... So how we would write this is S of peanut butter and jelly sandwich is 1. So the peanut butter and jelly sandwich has a degree of membership 1 to the set of sandwiches. Now, for the notorious example, we all knew it was coming. Raise the hands. Who all thinks a hot dog is a sandwich? My point exactly. This is why we need fuzzy sets to describe sandwiches, because there was about like 24% that said yes. And that is much better. We don't want it to just be black and white, because then those 25% of people are left out, So for those of you who didn't think it was a hot dog, maybe you're thinking, it's just got that weird vertical orientation. I ain't about this. It's not quite like a sandwich. Or if we allow a hot dog to be a sandwich, then a taco's got to be a sandwich. And that's just ludicrous. We don't want that. And those of you that do think it's a hot dog might be like, well, if you just take the buns and split them apart, there's no difference between it and a sandwich, like, come on. So me personally, I think it's about 7/8. I think as a hot dog is about 7/8. It's pretty close to a sandwich, but just doesn't feel quite right. So for an example, I could have went and assigned the membership to a bunch of different foods, but I thought that was kind of boring. So I decided to incite some chaos into my math department and took a poll. So I sent out a survey that had these 14 foods on it, and it had a scale from 0 to 10, and it was, to what percent do you think each food is a sandwich? And I took the average of each one, and these were the membership values. So I think we did pretty all right. I mean, a club sandwich, that's close to 1. That's pretty good. Frosted sugar cookie, rightfully where it should be, 0.2. I think it should have been at 0, but that's just me. And then hot dog, classically at 50%. Very controversial. That makes sense. And then keep in mind what we've done here. We've pretty much we've defined what a sandwich is, in a sense, right? I think this is a much better definition of it, given its vague nature. We don't want to say it either is or it isn't. It's allowed to be on this spectrum, So yeah. And you might be looking at this and saying, what in the world is this set? What does it mean for something to even be in this set, right? It's a set, so there's got to be points in it. So glad you asked. Let's talk about it. So next we are going to define a fuzzy point. And so a fuzzy point, x sub lambda, is defined as a fuzzy set, because of course it couldn't be a point. We had to make it more complicated. So our fuzzy point is a set with the membership function with 0 everywhere besides x, but at x, it has the membership lambda. And if a fuzzy point is in a fuzzy subset A, then that would mean lambda is less than or equal to the membership of x in the fuzzy set A. Now, let's take a picture of that. That definition was a little hard to read through. So here I have a picture where I've put 2 fuzzy points on our graph over there to show where they are in relation to all the other points. And notice that hot dog sub 0.5, its lambda is 0.5, which is less than or equal to 0.54. So by our definition, that point, hot dog 0.5, would be in our fuzzy set. And notice that visually, it is below the membership value. So that would naturally lead you to conclude any point that is below its membership value would also be in the fuzzy set. And like hot dogs of 0.9, 0.9 is strictly greater than 0.54. So it is not in the set, and it is visually above the membership value. So really our fuzzy set doesn't look like this. It looks more like this with all the fuzzy points included, where the blue bars represent all of the fuzzy points that are included in our fuzzy set of sandwiches. What a mouthful. Okay. So yeah, and I left the hot dogs on there so you can see that, yes, hot dog of 0.5 is indeed in that blue bar. So yeah. All right. So now that we have this notion of fuzzy points being in a set and what the points look like in the fuzzy sets, we can define all types of fuzzy operations of fuzzy set theory, like what a null set would look like, or universal set, unions, intersections, complements, subsets. And if you have a keen eye and you know any topology, you've noticed I've given you just enough set theory to start describing at least crisp topologies, assuming the definition is relatively similar for fuzzy topological spaces, which it is. You just changed that. Oh, that's supposed to be shifted over here. Subsets of U. You change subsets of U for fuzzy subsets of U. That's it. The rest of the definition is the exact same. So let's talk about it. Fuzzy topology and how it relates to sandwiches. Oh boy, that did not turn. Okay. All right. So for those of you who don't understand a whole lot of topology, there's 2 quick points that you are probably going to need to know for the rest of the presentation. So really what a fuzzy topological space is it's a collection of fuzzy subsets that define a notion of closeness on the universal set. And then with that notion of closeness, we could talk about a boundary, or a point is in the boundary if it is close to both being inside the set and not inside the set, roughly, topologically speaking. So if we look at an example in our friendly picture drawing topology, the standard topology on R, if we look at the set B there, if you take your intuition of what closeness means, you would probably guess the boundary of that set is the dotted circle around it, because those are the set of points that are the closest to being in the set and not in the set. And you would be right. All right, so let's talk about the boundary of a sandwich. And of course, everyone in the audience is probably thinking, well, of course, it's just the bread that holds everything in between. Oh, no, that can't be right. That can't be right. Yes, I said boundary of a sandwich. I meant boundary of a sandwich set. That's my bad. My mistake. So going back to our ESU set, which I've dubbed S sub ESU now, let's try to find the boundary of it in some fuzzy topological space. So this part's going to go a little quick. Strap in, folks. So first, we are going to need to decide what topology we're going to find it in. I chose the discrete topology because it is simple to understand. And now with that regular topology, we have to fuzzify it using that F sub U function. And this is the proof as to why it's a fuzzy topological space, which I wrote. And then you do a whole bunch of other nonsense with fuzzy interiors and fuzzy closures all the way to get to the boundary. There's the boundary. All right. So yeah, don't worry about that up there. Just look at the pretty pictures. So we got our ESU set and we got the boundary of our ESU set. And you might be wondering, well, why did we just do all of that? This seems rather interesting. So let's analyze this a little bit, right? So we notice some interesting point that you might notice is that we have Club Sandwich has 0.95 membership to the set of ESU sandwiches, but it is hardly in our boundary at all. And that's because if you remember our definition of boundary, the definition of boundary is the points that are both close to being in the set and not in the set. This point is really close to being in the set, but not close to not being in the set. It's not close to 0. So therefore, it wouldn't be in our boundary very much. And Frosted Sugar Cookie has the exact opposite problem. It's really close to not being in our set, but it's not close to being in our set. So it's not going to be in our boundary very much. And then if we look at something like Hot Dog, it's really close to 50%, which is the closest you can get to being both 0 and 1 at the same time. Right, makes sense. And if you take a look, all of the points that are close to 0.5 are really high in our boundary. So if we look at our boundary set, we can easily tell which points are kind of giving us trouble, right? A hot dog is very controversial. So about 50% of the population liked it, and it's really high in our boundary. Same with like a s'more. So yeah, this in a way gives us a way to start analyzing how good our definition is, because a lot of people would want a definition to be either really close, every food to be really close to a sandwich or not a sandwich, So this can kind of help us analyze what are the trouble points there. And the beauty of doing it in topology is that you can change the notion of closeness. And then that'll give you a different boundary, that'll give you a different way of analyzing the problem. So yeah, so that was a lot. Let's go back to the original question that we had here. What is the definition of a sandwich? Did we get any closer? The definition of a sandwich is, the term itself is so vaguely defined that I believe that it deserves an equally vague definition. And I mean, we've discussed tools today to represent how this vague definition could be constructed and analyzed to constructively have a conversation about how we should define sandwiches, All right. Thanks. All right. Questions? Yes.
You're talking about sandwiches with your fuzzy sets, and when you're looking at the sub collections of those, would those be sub sets?
Are you talking about subsets of the sandwich sets?
Yeah, like sub as in like sub sandwich.
Okay. Sorry, that took me way too long. That's my bad. Yes.
The hot dog is the most controversial of the things you presented. But it didn't have its boundary value close to 1. In the definitions that went kind of screaming by, perhaps is there something in there that says that there's a limit, or could you get close to one on something being really on the boundary?
Excellent observation. Yes, the points will only be equal to or less than a half.
Okay. So
Yeah.
really close to a half is really on the boundary.
Right, and that's exactly, yeah, that's why I like the half. Yeah, definitely. Great observation. Yes.
Speaking of fuzzy boundaries, how did you actually calculate?
The short answer to that, I guess, is so you use it, you use obviously interiors and closures like you do in any topology, and there are just fuzzy analogous concepts to those where you just flip, normal subsets to fuzzy subsets, and the definitions are virtually the same. So yeah, we would just do it similarly to regular topology, just with different sets, and they look different and act different. Yes.
Could you do the same sort of fuzzy definition for ingredients for sandwich? And then
I'm sure.
Something like bread would have a really high value, but the actual hot dog would then start having a lower value and so on.
Yeah, interesting question. Yeah, you could definitely, you could fuzzify pretty much anything, right?
Right.
As long as it's vague enough. So yeah, you could probably definitely do that. You'd probably have to change like the universal sets, or you might not even have to. Yeah, you probably could. You definitely could. Right. Yeah. I'd hope that'd be close to zero on this. Oh, okay. Well, okay. Fair enough. Fair enough. Yeah. Yeah. Those two people. Anyways. Yes.
I don't know, just because you'd seen the argument online or something else?
Yeah, so we were me and my professor who was advising my independent study on fuzzy topology. One of the another professor that's like next door to him came in one day and was started to talk about sandwiches and how vague that was. And the first chapter of the book that I used to get all of this talks about vagueness and defines vagueness. I was like, that's perfect. That'll be a perfect approachable way to explain it to everybody.
Building off of your question, so the idea is that it is vague, like you just said, and you're trying to decide like how much you're going to say it's in or out, and then at the end you actually get stuff that's like the hardest to decide, and which is really nice. I think that should, that if you set it up right, that's working. The thing you expect to be hard to decide are those high levels. So then my question is, the way that you decided how much something was in the set, you based in this case on survey data.
Yes.
So you could reconstruct this for anything that's hard to decide, as long as you have some metric such as survey data or some other metric to decide between 0 and 1 is the center out.
Precisely. Yeah, there are a lot of vague problems in life that could have that,
Okay.
So yeah, definitely. All right. All right.
Speaker.